In this video, we're going to take a look at the physics application of work. Now, you might be curious why we're studying physics applications like work in this particular point in the semester. Well, the reason for that is, in a general sense, work is computed using a definite integral, and we've been talking recently about definite integrals, so it would be a good time for us to have this discussion as well. So if we have a constant force, a force that doesn't fluctuate at all, most beginning physics students would know that work, the formula for work, is the force that's applied to a particular object times the distance that that force is being applied to that particular object. Okay. Now it's important to notice that this is for a constant force. That's going to change later in this video here. All right, now let's think about how we can interpret this here. I've got a picture here that I think will help us interpret this a little bit. Assuming that the force is in fact constant, you can think of this as a force applied over a given distance. So, common units would be something like, if the force is in, let's say, pounds and the distance is in feet, then one of the units for work would be foot pounds. There's an equivalent unit if your force is in, let's say, you're identifying the mass in terms of like kilograms and the force is in newtons and your distance is in meters, let's say, then you would have a newton meter, otherwise known as a joule. So there's different units for work depending on the units of your forces and your distance and those sorts of things. But at the end of the day, we see exactly why it's force times distance. Looking at this picture here, it's really the area under the curve. That's really what's going on here. Now that brings up an interesting question though. If the work is simply the area under the curve for a given force applied over a given distance, what happens if the force were to vary, right? Because, in a real life scenario, how likely is it for a force to stay exactly constant over the duration of this situation? Possibly not very likely. So what if the force was greater at some point and lower at others? And that would be a very good question. So let me actually sketch that out here real quick. Okay, here's a basic graph, and let's just say, for example, that that this is still force, a force that's applied over a given distance, right? The force applied over a given distance, but it gets larger and smaller as you move, across this distance that is traveling here. Well, it's still going to be the area under the curve, right? It's still going to be the area under the curve. This will be the total work done on a given object. So here's going to be our method to compute this here. You could actually start with, if you remember Riemann sums some while back, what we could do is we could take a sum from I equals 1 to n, where we break this guy up into a certain number of rectangles, and forgive me for being somewhat sloppy here, look something like that. And then the height of each of these rectangles depends on the force function. So it would be the force at a given x value. We'll say x sub I star. That's the force at a given x value in the ith subinterval times the width of the given rectangle. Now this would approximate the work done. So after this we would take the limit as n approaches infinity, and in other words, in plain English, we would let the number of rectangles get larger and larger and larger. Well, this notation looks very, very familiar to us. We're exactly sure what this is going to be. This would convert into a definite integral, and we know this from the videos on Riemann sums. So this would convert to an integral from a to b of f of x dx. And so really, in effect, we're getting the area under the curve. And so you compute this definite integral even if the force is fluctuating or changing, and this numerical answer will wind up representing the work done on an object as it moves over a particular distance with a particular force being applied to it.